So guys, we're going to take a look at section 9.2, which is where we get into talking about series. So we're taking those sequences we talked about in the last section, and now we're going to put them together and look at the series and what happens when we take a series to infinity. So don't write this down, but just take a look for a second. It says start with a square that's 1 unit by 1 unit. So the area of this square, of course, would be 1. If we cut it in half, and then we take the half that's there and cut it in half again, we get a fourth. And then if we cut that in half again, we get an eighth. And so what I'm doing is I'm taking half, and then a half, and then a half of that, and half of that. And if I add those together, what should that add up to? Well, it should add up to 1 because that was the area of the original square. Now I can keep taking each piece and cutting it in half, and then cutting it in half, and then cutting it in half. And theoretically I could do that to infinity, but the sum would be 1. So this would be an example of an infinite series. We would say that this series converges. In other words, the sums approach a limiting value of 1. A lot of series do not converge. So this series, there's a special name for this which we'll talk about in a later section, but if we just take the series 1 plus a half plus a third plus a fourth plus a fifth, these sums will never approach a limiting value. They would just keep adding up to bigger and bigger numbers. Kind of like at the end of chapter 8 when we talked about improper integrals and we talked about areas. And when we add up those areas, do those areas approach a limiting value, in which case we say that the integral converged, or do they just keep getting bigger and bigger, in which case we said the integral diverges. It's the same idea. We're just looking at these series, and if the sums don't approach any kind of a value, we say that the series diverges. An infinite series, the notation, so this you want to be familiar with and be comfortable with. We use sigma to represent the symbol for an infinite series. We generally start the series at 1, although it doesn't have to start at 1, but oftentimes it does. Sometimes it starts at 0, depending on the way the series is written, and then we take it to infinity. The sequences, or the terms rather, of the sequence would be written a sub n, so that would be like a sub 1 plus a sub 2 plus a sub 3 up to wherever we stop at. This notation, this is called a partial sum. So a capital S with a little 1 subscript would be the first partial sum. That would just be the first term. S sub 2 would be what we'd call the second partial sum, which would be the sum of the first and the second term. S sub 3 would be the sum of the first, second, and third term, and so forth. And we could go up to S sub n, and we would call that, we would call that the nth partial sum. So S sub n would be the sum of whatever n terms we decide to stop at. In an infinite series, and now I'm using the same notation, a sub 1, a sub 2, etc. are the terms of the series. A sub n we would also call the nth term of the series. And then, like I said, those partial sums we just looked at would be called, would use that notation with a capital S. And S sub n, again, would be the nth partial sum. So this notation, see if this makes sense to you. Another way of writing, let me back up one slide for just a second. Right here, another way of writing out the nth partial sum, instead of a1 plus a2 plus a3 dot 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 up to a sub n, a way of writing that using series notation, let me show you that again, right here, this would be using the sigma notation. That would be the sum from 1 up to n. I'm using k, I could use I, it doesn't matter what variable I use, but if I add up the sums from 1 up to the nth term, or the sum of the terms from the first term up to the nth term, that would also be another way of saying our nth partial sum. If S sub n, or the nth partial sum, has a limit as n goes to infinity, then we say that the series converges. So in other words, if we add up those sums, and the sums that we get as n gets larger and larger, so if we add up the first 10 terms, the first 100 terms, the first 1,000 terms, the first 1,000,000 terms, those are all partial sums. If those sums all approach a number, or they approach a limit, a limiting value, that's when we say the series converges. Otherwise, we would say the series diverges. So let's do an example. This says find the nth partial sum of this series. So we've got the sigma of 1 over 2 to the n from 1 to infinity. So we have an infinite sum here, and they want us to come up with an expression for the nth partial sum. So let's look at another way of writing this, just for some clarity, and we'll see why we're doing this later. Note that we could express this 1 over 2 to the n as 1 over 2 quantity to the n power. And again, I'll show you why we're doing that in a few minutes. So what would the first partial sum be? Well, the first partial sum is just the first term itself because there's nothing to add to it. So in this example, that would just be 1/2, right? 1/2 to the first power. The second partial sum would be the first term plus the second term. So that would be 1/2 plus the second term when n is 2 would be 1/2 squared, so that would be 1/4. And we add those together, we get 3/4. The third partial sum, what would that be? That would be 1/2 plus 1/4 plus 1/8. So when n is 3, this would be 1/8. And we add those together, we get 7/8. Let's do one more. S sub 4 would be the sum of the first 4 terms, and that would give us 15 over 16. So hopefully looking at these terms, these sums rather, you've got 1/2 for the first partial sum, 3/4 for the second partial sum, 7/8 for the third partial sum, and 15/16 for the fourth partial sum. Hopefully you see that there's a little bit of a pattern here. And you notice that all of the denominators are 2 to the n, right? So whatever n is, 2 to the n. So like the fourth partial sum, n is 4. 2 to the fourth is 16. Third partial sum, n is 3. That gave us 8. 2 to the third, and so forth. And notice the numerator is 1 less than the denominator. So we could express the nth partial sum as the expression 2 to the n minus 1 all over 2 to the n. What is the infinite sum then for that series? So to get the infinite sum, that would mean we would take the limit of the nth partial sum. So let me go back for just a second. Remember, this was our expression for the nth partial sum. We said it was 2 to the n minus 1 all over 2 to the n. Notice that that can be simplified into 1 minus 1 over 2 to the n. Make sure you see where that's coming from. If you separate these into two separate fractions, 2 to the n over 2 to the n, of course, would be 1. So we have 1 minus 1 over 2 to the n. So if we take the limit as n approaches infinity, that would do what to this denominator? This denominator, 2 to the n, would get larger and larger, so this fraction would approach 0. And so our limit would be 1. So we would say the sum of this infinite series would be the limit of the nth partial sum, and we just calculated the limit of the nth partial sum to be 1. So we would say that the series converges to 1. This is also a special type of series that we're looking at called a geometric series, and that's going to come up quite a bit. So a geometric series is a special type of series, and it's a series where each term can be found by multiplying the preceding term by a particular number. We usually use r to be that multiplier, and another name for that is the common ratio. You might have seen geometric series back in high school, maybe in Algebra 2, but that's probably the last time we actually talked about the term geometric series. They're always in the form sigma, and then it's a times r to the n. Now there can be some variation to this. It might be r to the n minus 1. This series, the way I've written it, is starting at n equals 0. However, it could start at n equals 1. The point, though, is that you've got some common ratio r that you're multiplying to get each subsequent term. And so r to the n is what tells us this is a geometric series, or r raised to some power. This is an important fact about a geometric series, is that we can always tell if the series is going to converge or diverge based on what the r value is. So if the absolute value of r, and I'm using absolute value because r could be negative, that's called an alternating geometric series, which we'll get into later in the chapter. But if the absolute value of r is less than 1, then that means this infinite series is going to converge. And we know that it's going to converge to a particular infinite sum of a over 1 minus r. If the absolute value of r happens to be greater than or equal to 1, then the sums will just keep getting bigger and bigger and bigger and bigger, in which case we'd say that the series diverges. Another name for r is the interval of convergence, and we'll get more into that later in the chapter, that term, interval of convergence. But the interval of convergence in this case is as long as r is between -1 and 1. Where am I getting that from? Right here, because we said the absolute value of r has to be less than 1. That's called the interval of convergence. Let's do an example here. So we have the infinite sum 3 over 10 plus 3 over 100 plus 3 over 1,000, etc. Notice I'm not using sigma notation, but I can tell this is a geometric series because there's a common ratio. In other words, to get from 3/10 to 3/100, what would I multiply by? And likewise, to get from 3/100 to 3/1000, what would I multiply by? Hopefully you see that that would be 1 over 10, right? So if I multiply 3 over 10 by 1 over 10, I get 3 over 100. Multiply by 1 over 10 again, I get 3 over 1,000, etc. I took each of these and wrote them as decimals. So 3/10, of course, would be 0.3. 3/100 would be 0.03, etc. And that would add up to 0.3 repeating, just 1/3. And so what do we have here that we're working with? We know this is a geometric series because the common ratio to get from one term to the next was 1/10. The first term was A. Let me make one more comment. I don't think I said this very well. Back here in this formula. A over 1 minus R, that's the formula you want to pay attention to find the infinite sum of a geometric series. A is the first term of the series. In my expression here, n equals 0 is where I'd start the series at. So r to the 0, of course, would be 1. That means just A, or just A here, is the first term. So basically, it's the first term of the series divided by 1 minus whatever the common ratio is. That gets you your infinite sum. So that's what I'm applying here in this next example. Let me show you what I mean. So the first term of the series in this case was 3 over 10. That's the A value. And the R, the common ratio, was 1/10. That's how I got from one number to the next, multiplied by 1/10. So if I put this into this infinite sum formula, A over 1 minus R, 3/10 over 1 minus 1/10, that's A, and that 1/10, of course, is your R. So that gives me 3/10 over 9/10 when we get a common denominator and simplify, and that gives me 3/9, which is 1/3. We knew the sum was 1/3. When we write it in a decimal, we can see it. But I want you to see an example of an infinite geometric series that does converge because the common ratio was 1/10, which is less than 1, and it got us to the infinite sum of 1/3, which is what we are expecting. Let's do another example. So here we have a geometric series. This is an alternating geometric series because it alternates in signs. How do I know it's geometric? Because to get from one number to the next, I'm going to multiply by a common ratio. Can you tell what the number is that I'm multiplying to get from one number to the next? In other words, 1 times what gives me negative 1/2? Negative 1/2 times what gives me 1/4? It should be the same number. And hopefully you see that that's negative 1/2. So the common ratio is negative 1/2. We know it's going to converge because that's a number that's less than 1. The absolute value of it's less than 1. The initial term is 1, so we're going to use that formula, A over 1 minus R. And so that gives me 1 over 1 plus 1/2, which is 1 over 3/2, which gives me 2/3. So my infinite sum here is 2/3. The nth partial sum of a geometric series. All right, so now let's pay attention to what we're talking about here. So we just looked at in the last two examples the infinite sum. So the infinite sum, if this series converges, it converges to the infinite sum of 2/3. If we don't want to go all the way to infinity, if we want to stop at a particular value, say we want to look at the 10th partial sum or the 50th partial sum, that would be the sum of the first 50 terms, for example. The formula we can use for that with a geometric series is this formula right here. So S sub n, the nth partial sum, is equal to A, the initial term, times 1 minus R to the n all over 1 minus R. We'll be asked to do some things with this. So this is a formula you're going to highlight and have in your notes so you can use it when you need it. From this you can see where the formula for the infinite sum series comes from, and if R is a number less than 1, R to the n power, the limit, remember we said to get an infinite sum, it's the limit of the nth partial sum. So if n goes to infinity, this goes to 0, which just leaves me with A over 1 minus R. So that's where that infinite sum formula we were working with a few minutes ago, that's where it comes from. It's the limit of this nth partial sum formula. So find the partial sum of this series. So we've got 1 over n minus 1 over n plus 1. Now, this one's a little bit different. We're not looking at a geometric series here, so let's just write out the first few terms. How do I know we're not looking at a geometric series? Because it's not in that format for a geometric series. Let me go back just a couple of slides here. It's not in that format of AR to the n, where you have some r raised to a power. This one's a little bit different. Let me go back to it. Here it is. This one's a little bit different. So to find the partial sum for this series, let's just write out a few terms and see if we can come up with a pattern. So notice this series starts where n equals 1. So the first terms would be 1 minus 1 over 2. The second term where n is 2 would be 1/2 minus 1 over 3 plus 1/3 minus 1 over 4. And then it would follow that pattern. And hopefully you notice that all of these terms in the middle will zero out. The negative 1/3 and the positive 1/3, those cancel out. The negative 1/2 and the positive 1/2, those cancel out. The negative 1/4 with the next 1/4, those would cancel out. And this 1 over n would cancel out and just leave you with the first term and the last term. So the nth partial sum for this series can be expressed as 1 minus 1 over n plus 1. It said find the partial sum, so let's take the limit of this series as n approaches infinity. So we've got 1 minus 1 over n plus 1. We're going to take the limit. What happens to the second term? It's going to go to 0 as n gets large, and so I'm just left with 1 for the sum. Remember, the infinite sum is the limit of the nth partial sum. So if I can come up with an expression for the nth partial sum, and I can take the limit for that and get an answer, a number that makes sense, and it's not infinity or something like that, that tells us that the infinite series converges. I think this question maybe wasn't the right question. It says find the partial sum. Well, we did do that. We found an expression for the partial sum. But we actually went a step further and we found the infinite sum. So the infinite sum for this series is 1. It converges to 1 because we were able to find an expression for the nth partial sum and we were able to get a limit for that nth partial sum. That last question is an example of a telescoping series. So a telescoping series you can recognize because they're often written as the difference of two terms, so like b sub n minus b sub n plus 1. And often when you have a telescoping series, those middle terms will cancel out. What I would recommend is that when you notice something is telescoping or you suspect maybe that it's telescoping, write out a few of the terms and see if you can see a pattern where those middle terms cancel out. We can always find the partial sum of a telescoping series by doing what we just did. So write out a few terms, see if you recognize the pattern, and you're often left with the first term minus the n plus 1th term at the end. And then again, if we can get a limit for that expression, then that tells us that telescoping series converges. Let's try this one. It says find the sum. Oops, let me move this up so you can see it. Find the sum of the series 2 over 4n squared minus 1. And we're taking the series from 1 to infinity. We can write this as a telescoping form using partial fractions. So at first glance, it may not look like a telescoping series because we're not taking the difference of two things. But notice that the denominator factors into 2n plus 1 times 2n minus 1. So if we break this down and use partial fraction decomposition, remember from the last chapter, and I'm skipping the details here, but this will simplify into 1 over 2n minus 1 minus 1 over 2n plus 1. So our nth partial sum, if we write out a few terms, just to get a sense of what's happening, notice this started at n equals 1. So the first term would be 1 minus 1/3. The second term would be 1/3 minus 1/5, and so forth. And what would happen? Write a few more terms out so you see the pattern. What would happen is all the terms in the middle would cancel, and we'd be left with the first term and the last term. So to find the infinite sum of the series, the question is, what is the limit of this expression I have now for the nth partial sum? And so that limit would be the limit as n goes to infinity of 1 minus 1 over 2n plus 1. Of course, this 1 over 2n plus 1 will zero out, and that just leaves us with 1. So that tells us that the original infinite series converges to the value of 1. All right, it says find the sum of this series, and it says if it exists. So what I want you to notice is this looks kind of like a geometric series. And by the way, as we go through this chapter, start thinking about what are the types of series we have learned so far. We're going to have a bunch of different types of these infinite series. You want to get comfortable recognizing the different formats when you see them. So far, what have we done? We've done geometric and we've done telescoping. Those are the only two we have so far. I don't think this is telescoping because there's nothing that looks like it's being subtracted. I just have a single term, so it must be geometric. So how can I get it in a form I'm a little bit more familiar with? Well, I would maybe rewrite it so that the 3 is in front, and that leaves you with 1 over 2 to the n, which can be written as 1/2, all raised to the n power. I like writing that 1 over 2 to the n this way because that helps me really see what the common ratio is. And hopefully you see that the common ratio is 1/2. The value we're going to multiply by is 1/2. And then since n started at 0, the initial term would be 3 because it would be 3 times 1/2 to the 0 power, which of course would be 1. So we know that the series is going to converge, and it's going to converge to the sum of a over 1 minus r. So that would be 3 over 1 minus 1/2, which is 6. So this is a geometric series that does converge, and it converges to the infinite sum of 6. And by the way, I think there is a little typo here. This shouldn't have an n there. This is the infinite sum, not the partial sum. So this n should not be here. Cross that out in your notes. It should just be s. The infinite sum is equal to a over 1 minus r, which is 6. How about this one? So make a little bit of a difference in comparison between this one and the last one. Looks similar, but notice it's 3 over 2 being raised to a power. So this is still geometric. However, the common ratio is 3/2, which is greater than 1. So that tells us right away that this diverges and there's nothing we can do. Use a geometric series to express this repeating decimal as the ratio of two integers. So note that we can rewrite this as 8 over 10 to the second power plus 8 over 10 to the fourth plus 8 over 10 to the sixth, etc. And that can be written as a geometric series where if we start at 0, n equals 0, the initial term is 8 over 10 squared, and then the common ratio is 1 over 10 squared to the second, or to the nth power. And so our common ratio is 1 over 10 squared. Since that's less than 1, of course, this is going to converge. So I'm going to use the infinite sum formula, a over 1 minus r. So we have 8 over 10 squared as the initial term, divided by 1 minus 1 over 10 squared. If we clean that up, do some simplification, we get 8 over 99. If you get your calculator out and look at it and do 8 divided by 99, it'll give you this decimal. Last thing I want to talk about is something called the nth term test for divergence. So as we go through this unit, we're going to have a lot of different types of series. Like I said, you're going to want to get comfortable at recognizing the different types when you see them. And the question, the overarching question, is often going to be, does this series converge or diverge? And so this, other than what we've done so far, so we have geometric series, and we can tell if it's geometric whether it converges or diverges by looking at that r value. If it's telescoping, we can tell if it converges or diverges by looking at that nth partial sum, writing out the terms, and taking its limit. Now this is the next test we're going to have, which is to tell if a series diverges. So it says, note that the first requirement for a convergence of a series is that the terms of the sequence a sub n must approach 0. In other words, if this series is going to converge, this infinite series, then the limit as n approaches 0 of a sub n, whatever this term is right here, it has to be 0. So the contrapositive of that statement actually gives us a test that we can use to tell if a series diverges. So this is the part you want to pay attention to right here. If the limit of as n goes to infinity of a sub n is not 0, so if in other words, if that limit goes to anything other than 0, that's a sign that the series diverges. Now if it goes to 0, it doesn't necessarily mean it converges or diverges, it just means the test fails. But this is a test for divergence. So if you can tell right away that this limit is going to go to anything other than 0, then that indicates that it's going to be diverging. The series is going to be diverging. So it says, notice we were talking about the limit of the sequence, not the partial sum. So this time for this test, I'm only looking at whatever a sub n is, whatever this term is without the sigma. That's what we're looking at the limit for. Let's do an example. Determine if this series diverges. Now, before I get too involved, hopefully you see that this actually is a geometric series because you have something raised to the n power. And the common ratio is 2, which is greater than 1. So that tells you it diverges. But if we looked at the sequence 2 to the n, and we took the limit as n goes to infinity, well, 2 to the n is just going to get bigger and bigger and bigger. It's an exponential function, and the limit's infinity. So this tells us that because this is not 0, we could say that this series diverges by the nth term test. So it happened to be this was geometric, but even if it wasn't geometric, as long as you see that this limit of this series, or this limit of this term, is anything other than 0, you can say the series diverges. Look at this example. Now, we haven't talked about factorial notation. I think we mentioned it in the office not too long ago, but remember, if you see n factorial, that's n times, like if it's n factorial, that would be, like say 5 factorial, that would be 5 times 4 times 3 times 2 times 1. So what could we do with this series? Well, let's look at the limit as n goes to infinity of just this a sub n term. And so you can kind of think of this like growth rates. We've got n factorial and n factorial in both the numerator and the denominator. So they're growing at the same rate. And remember we said if you have a rational expression and you're taking the limit as n goes to infinity, if the numerator and the denominator are growing at the same rate, you can look at just the ratio of the leading coefficients. So this is 1 in the top, 2 in the bottom, which gives us a limit of 1/2. So what does that tell us? That tells us that by the nth term test, this series diverges because this limit is not 0. Let's try this one. So we've got the limit of 1 over n as n approaches, or the limit, let me try it again. The series of 1 over n as n goes from 1 to infinity. So we can try the nth term test here. The limit as n goes to infinity of 1 over n. But what's going to happen here? This is going to go to what? This limit is going to just go to what? It's going to go to 0. What does that tell us? That doesn't tell us anything. So if you take this limit and you happen to get 0, that means the nth term test fails. And that means we can't say whether this diverges or converges. So I just want to point out that just because you get 0, don't default and say, oh, then it converges. That's not the case necessarily. In fact, this series diverges, and we're going to talk about this later on again, this particular series. But if you get 0 for that limit, that means the test fails. The only way we can apply the nth term test is if this limit goes to anything other than 0.